Oh, good morning, everyone. All right, well, welcome to yet another episode of Water Systems Design. Today we take a distinct change from the first two parts. The first part was drinking water system distribution. So that was taking water, making it yummy, and then sending it to customers through pipeline networks. At the same time, we had stormwater collection system, which was to take stormwater from rainfall, if you will, and directing its runoff in such a way as to not inconvenience civilized infrastructure going on around it, prevent flooding so their streets will work, and so forth. But now we're at the last part, which is after that yummy water that we drinking water distributed has been processed by kidneys and colons, return it back to the system. So first we want to collect that water, which for reasons that make no darn sense at all, it's called sanitary sewage. There's nothing sanitary about it if you get stuck in it. But it was historically, it was called a sanitary sewage because by keeping it separate from other things, we enhance the sanitary nature of our environment. And then that goes on to a treatment plant, which is the subject of a whole nother master's degree in environmental engineering, and then finally leaves the treatment plant and usually is returned to a receiving stream at various prescribed or permitted constituent standards. Okay, so let me get to the class website. I was working on it a bit this morning because the server failed yet again. And it should be, let's see, let's go Blackboard. Yep, Blackboard one failed too, didn't it? Yeah, sure enough. Okay, let's go ahead and add the quick content. This won't take very long. Okay, that should let you all get there whenever you're ready. And let's go ahead and test the link. Yay. So the topic of this lesson, this will be Actually fairly interesting lesson. It's kind of, today is just a brief overview. It's sanitary system, collection systems, and the hydraulics associated with such things. So in the notes, we have a PDF rendering from, let's see, 404 on the 11th, the 10th, is that right? There's something wrong with the timing on my machinery. That's not what I expected to see. Let's see what lesson 22 is. At least get the naming convention right. Oh, right. So today's lesson is a quick overview of sanitary sewer systems. On Thursday, we'll examine one or more design guideline documents, something like we have for drinking water systems, which was RG 195, and we looked at a few other ones that were jurisdiction specific. We did a similar examination for stormwater, and we'll do a similar one for sanitary sewer systems. But let's go ahead and refresh our memory on what these things are. So collection systems in general, they're used to collect wastewater and deliver it to some common location. In the case of sanitary wastewater, or what we know as sewage, that location is pretty much going to be some kind of treatment facility, and then after treatment, it's diverted onward towards an outfall. For stormwater, which we've already examined, we would we would break that that prior bullet item, and that we don't necessarily treat stormwater, and we'll collect it and direct it directly to an outfall or to a receiving stream. That philosophy is changing, and we are implementing more and more relatively small scale features in a drainage network whose purpose in life is indeed to confer some kind of water quality benefit on that stormwater before it gets to the receiving stream. These systems play a pretty important role in the control of water quality. In the absence of a sewage collection system, it would pile up in your backyard until the fly count would be undesirable. More practically, historically, at least in urbanized areas, the sewage was thrown into open sewers and gutters and ran down the streets. So you could imagine what the smell would be like. If you've ever had the chance to travel to other countries, you can get a pretty good example of what a city would smell like if you're in Amsterdam when there's a pretty good storm and the sewer systems overflow, and it puts a little bit of sanitary sewage into the street. It does that here too. It's pretty uncommon, but the stench is phenomenal. And the only reason I say Amsterdam is that's a city that's on the order of thousands of years old. Maybe not quite that, but quite a bit older than any city in the United States. So there's a lot of backed up sewage, if you will. And then I'm trying to think, I once visited Mexico City, but I was pretty close to a pump plant. So the sewage by intent had come up to the surface and was running in an open channel. And the odor was overwhelming. And you wanted to get upwind of it as soon as you can before it knocked you out and they just add you to the sewage. So we want to keep our sanitary systems contained because it has an important benefit in water quality and basically protects all of our health. What these systems do is they concentrate certain kinds of potential non-point source discharges into a single location, a point discharge. And once it's a point discharge, we can often manage the quality and quantity quite a bit more efficiently.
Dr. Cleveland, sorry to interrupt, but could you start sharing your screen?
Oh, I'm glad you interrupted me now. Yes.
Yeah, I was just about to ask.
I'm just blithely going away. Yeah, you need to interrupt sooner when that amount of stupidity happens on my part. Oh, good. Well, then you didn't see any of that stuff, although it is recorded. That's a good thing. Okay, so here's the first slide, and here's the second one. The importance on this is that oh, it's not going to function today. Sewage goes to treatment and then to an outfall. Stormwater goes to outfall. That's the only difference in this slide. And then collection systems are important in water quality. And what they're intended to do is to take distributed discharges or non-point discharges and concentrate them into a single point or a handful of points, which can be managed more efficiently. And so that begs the question, what's point and non-point sources? So you may have had a picture like this in your environmental engineering class. You may have even had this very picture, although I doubt it, because I steal it from different places than they steal. Well, this is just not going to go away, is it? There you go. So here's a picture of point and non-point sources, and the rather cynical or facetious statement here is point sources are called that because you can point to them. And that seems kind of absurd, but that's not a bad mental image. And non-point sources are things that are distributed over an area. So here we have a beautiful part of somewhere USA, a little bit downstream of our somewhere USA. And there's a factory. And this is where they make chocolates for Christmas time. And the leftover chocolate wastewater it leaves this pipe and goes into this receiving stream. Here's a wastewater treatment plant that takes everything from somewhere USA in the city, treats it, makes it yummy, and also puts it into the stream. So these two pipes discharging into a receiving stream, those are clearly point sources. For one thing, there's a label here that's pointing to them, but more importantly, because they're readily identified locations where wastewater is discharged into the environment. Over here we have cropland, animal feedlots, and rural homes, nicely zoned in this particular drawing, unlike real life. And these are called non-point sources in that rainwater, if you will, falls on this and makes its way out to the stream, and maybe it discharges right there, or maybe it discharges right there, or maybe between the two. My poor little computer is just having conniption fits. So there's a somewhat distributed discharge. So we don't know which of those four red arrows is going to be manifest in any given instance of a discharge event. Similarly with the animal feedlot, given that animal feedlots are probably not going to be exempt from certain water quality requirements in the near future, depending on which way the pigs are stomping, it could be that arrow or that one or that one. So non-point doesn't necessarily mean you can't point to it, but it means that the actual location of the discharge at any moment in time is unknown. Similarly for the rural runoff and the city street runoff and animal feedlots. Now, somewhat deceptive in this particular drawing is it's likely that our Somewhere USA subdivision is going to drain to a single point by design. Similarly, our city is going to drain to a single point. Rural homes, don't know. Cropland, animal feedlots, clearly non-point sources as per the usual definition. Now the types of sewers, this is not that varied. Essentially, we have separate sanitary sewer systems and something called a combined sewer system. We won't look at actual pictures of both of them, but we'll discuss them coming up. They're an important class of open channels, which you already know. They're usually underground, and they're used to transport wastewater both to the treatment plant and then to its final release point back into the environment. The usual design life or service life is on the order of 50 years. And so, like with drinking water and stormwater, we have to account for changes in population over their expected design/service life. In sanitary sewer systems, the individual discharges are collected, concentrated in the volume sense, and then delivered to a treatment plant for further processing. Storm sewer systems, individual discharges are collected, concentrated, and delivered to a receiving water. So those are almost identical sentences with the exception that one has a treatment process and one doesn't. A third type is called a combined sewer system. And this is a sanitary system that's designed also to collect stormwater. Now in the United States, new combined systems are not built. In fact, I believe new ones wouldn't even be permitted. They would violate probably EPA rules and a few others. But the older cities in the United States, those that were comparatively large in say the 1880s, already have combined sewer systems in place, and it would have been cost prohibitive to tear them up and go into separate sewer systems. And I'll show a map in a second that will show where the combined systems are in the US. So here's a hard to perceive map in the US. And the Northeast Seaboard, the Ohio River Valley, northeast. Ohio River Valley, a little bit to the west of that, we have, it's got to be, I get my Georgias mixed up. One of these is going to be Atlanta, one of them is going to be Savannah, and I forget what the other one is. And we move all the way to the west coast, San Francisco, Sacramento. So San Francisco is where I come from. And then you've got Portland, Oregon area, and Seattle, and this Bremerton area on the Pacific Northwest. Most of the central part of the United States, there's none in Texas, are separate sewer systems. So San Francisco is a combined sewer system. One of these here in New York somewhere is combined, and then a lot of the cities in the Ohio River Valley part of the United States have combined systems. So these have not been replaced. Oh, another major one here, they've been in the news a lot lately. Philadelphia has a fairly extensive combined sewer system. So you wouldn't do a new design for these. You wouldn't be allowed to. And a lot of the engineering involved on these combined sewer systems is identifying the cross connections and over time removing them as repairs have to be made. So the challenge in the combined system is not handling the sewage. The sanitary sewage is pretty predictable. The challenge is handling all that stormwater that comes in, and you would think that diluting things is good, which generally it is, but now that water by statute is going to have to pass through a wastewater treatment plant. And so you get these enormous volumes during storms that are essentially unmanageable. They can't be treated because the plant isn't big enough. And so the current thinking is we don't want to do that in the future, and we build separate storm sewer systems and sanitary sewer systems. So I bring this to your attention mostly because it's likely that some of you in your career will either live and work in these particular areas or have engineering contract jobs that involve work in these areas. And if you're doing sewer work, you need to be aware of the differences between combined and separate. So sewer categories basically share similar hydraulics. So the hydraulics of open channel flow, the hydraulics of storm sewage are essentially the same as the hydraulics of sanitary sewage. The main difference between storm and sanitary is the solids content and the fact that sanitary sewage has pathogens in it that are contributed by the various kidneys and colons along the way. They're topologically similar. They're comprised of pipes, boxes, junctions, lift stations, weirs, and various other features. And many of the design principles are interchangeable, although the sewer's ultimate purposes are strictly quite different. So the purpose of a sanitary system is to protect public health by isolating wastes from the environment until they can be treated and the reclaimed water released. So that brings up an interesting word. So the water in sanitary sewage, you'll see this word reclaimed water, and that's what they mean. They mean the treated water from the sanitary sewage, and then the residuals is what's left over, and that has to be dealt with in other ways, landfilling, coating it in chocolate and then selling it on the street, whatever's effective and legal. So when you see the word reclaimed water, it most often means water that was sanitary sewage that's been treated and now it's been reclaimed for higher beneficial use. It's not like the same thing as if somebody steals your water bottle and then you go grab them and you reclaim your water. Although that would be correct use of the word reclaim, but not the context we're talking about. A storm system protects public health by removing nuisance flooding, keeping infrastructure serviceable during all but the most severe weather. And as I've said before, in the last couple decades, storm sewer systems have been called upon to confer water quality benefit as they're collectors that capture that non-point pollution. If we return back to our other cartoon, these non-point portions, those generally spend their time in our storm sewer system. And so we're leveraging that knowledge as a way to increase the water quality of those little red arrows before they actually get to the receiving stream. So that's what this last bullet item means. So we'll now talk mostly about sanitary sewers. Sanitary sewers are pipeline systems underground that collect and transmit sewage from distributed sources to a central location. That central location is usually a treatment plant, although I suppose it could be a storage tank of some kind, and then it moves on further downstream to treatment. The pipes are usually operated as open channels, and they're not supposed to flow full. Gravity is the main driving force. Keeping in mind that statement, visualize for a moment, if you will, what would happen if a sanitary sewer system, if the pipe did actually surcharge. That means that the water surface elevation, if it could, would want to lie above the top of the pipe. That wouldn't bode very well if you happen to be in the vicinity of where that sewage came flying up out of the ground. And that happens in real world from time to time. And it's a good form of job security for hydraulic engineers if you're into it. Okay, gravity's driving force. In some portions of the system, the sewage has to be lifted to maintain flows towards a central plant. And these locations are called lift stations. Sewage on the discharge side of the pump flows in a pipe that goes by the name of force main until the pipe can return to open flow. Then it's just a sewage pipe. So again, we're bringing some jargon here, but when you see or hear the terminology force main, all that really means is a pipe that's on the discharge side of a pump that still is pressurized, and it's just some old jargon in the sewage industry, and the jargon's not going to go away, so we just have to adapt. The actual pumping stations, they're usually called lift stations, distinguished from a stormwater pumping station. If the word pumping station is used, it usually is referring to either stormwater or raw water. The rules of design are governed by federal law, state law, and most places municipal laws. And the various laws, codes, and guidelines that prescribe materials, joints, and labeling, etc., will vary from jurisdiction to jurisdiction slightly, but the broad principles of design are fairly uniform. Almost all sewer systems have to be engineered, which is a fancy way of saying that a professional engineer is involved with the design, or a licensed professional of some kind. And they can't, in a legal sense, be designed without professional interaction. So as an example, on a small on-site system, my wife and I years ago installed a on-site treatment system at a place on the coast, and literally it was a big pile of dirt with a septic system leach field put into the pile of dirt, and that was the main scientific purpose of that was that pile of dirt increased the distance the sewage water had to flow before it got to the water table. So there's nothing wrong with that. But getting a bulldozer out, making a pile of dirt, putting pipes in, any idiot could do that, as evidenced by the fact that that's what I did. But before we could turn it on, we had to have the county licensed on-site professional for that particular county come and check the work, and in fact checked all the design drawings, and then agreed that the as-built was the same as the design from North Carolina State University that we followed, and that is what made it legal to operate that system. So sewer systems are almost always professionally designed. So when we get to sewage characteristics, it behaves hydraulically pretty much like water. 5% solids by mass is typically the upper limit of raw sewage. So raw sewage with more than 5% solids by mass is unusual, and you're kind of approaching a slurry at that point. And then by volume, the percentage is usually quite a bit smaller, about 0.05% solids by volume. And the mention of solids is important because the solids collect in the system over time. Now remember those combined sewer systems in that map? So cities like Paris, New York, London, and so forth have combined sewer systems. They're old cities. And back in the day, from time to time, the solids would have to be cleaned out. And so here's a sketch of cleaning out a sewer in Paris. And so what they do is they stack up a bunch of baguettes that were too hard to eat, and that's to hold all the sewage flow back. And they open up the manhole cover, and as in proper confined entry, you have 3 workers underground, 1 guy above ground, and 1 guy putting the piles of residuals into a wagon. And they're shoveling the residuals into buckets, lifting them up, and then carting them away in the wagon, probably to some nearby bakery to sell to the aristocracy. So the best place in this whole picture to be would be this guy right here, who's right there on the head of the big old pile of residuals, shoveling it away, handing it to this guy, and handing it to this guy. The reason you want to be this guy up here is he doesn't have to take crap from anybody, whereas the guy down here is taking crap from all of his co-workers and putting it into the back of the cart. So that was kind of a pun right there. So I hope you've got the humor in the pun. The main point being is these solids collect, and based on this drawing, I mean, that's quite a log jam that they're working on right there. And if that sewer were to get any further clogged, there'd be no way for the wastewater to make its way away from whatever community this sewer is serving. So solids are still a problem today. They still collect in sewers. And so one of the principles of sewer design is to be sure that the flow velocities are high enough that the solids keep being transported over time, but low enough that that solids-laden water doesn't become essentially a liquid sandpaper. And so that's kind of the synthesis of the 2 to 10 foot per second design flow velocity. So the design engineer is concerned with the sewage quality itself insofar as it affects corrosion and safety to the maintenance personnel. So one of the added challenges with sanitary sewer design is that the quality of the sewage has a impact on the corrosivity of the sewage. Less so for stormwater and certainly not for drinking water. In those latter 2 contexts, we don't worry so much about corrosion. I mean, surely it must exist, but it's not something that we specifically spend a whole lot of worry about designing. With drinking water, to some extent, yes, with cathodic protection of different vessels. Perhaps the same with stormwater, but in the case of stormwater, we're more worried about the solids tearing things up. But with sewage, we are very concerned about corrosion because we're putting large diameter pipes underground. And if we have corrosion and it eats away at the pipe until pretty soon there's no pipe, then all of this stuff here can fall into the sewage and we get a sinkhole. In case of sewage, it's also known as a stink hole. And ironically, the corrosion doesn't occur necessarily at the top of the pipe, but it occurs somewhere on the haunching because the sewage is high in sulfur reducing compounds, and so it essentially makes the sulfuric acid, and that's in the air phase, and that starts to work away on the cementitious material in the pipes that support it, and over time you lose both the bottom of the pipe and the top of the pipe, and these things they fail fairly catastrophically. It's not common, but it's common enough that we worry about it. And to the point that in the Texas code, there's some discussion of corrosion and odor issues. and we're just going to look at some pieces. So one of the things the design engineer is concerned with in Texas is if a pipe or an integral structural component of a pipe will deteriorate when subjected to corrosive internal conditions, or if a pipe or component does not have a corrosive resistant liner installed by the pipe manufacturer, the report, this is your design report, must demonstrate the structural integrity of a pipe during the minimum 50-year design life cycle. In part B of this same section, we'll study this section on Thursday. A pipe must have an appropriate lining if the corrosion analysis indicates that corrosion will reduce the functional life of the pipe to less than 50 years. And there was no statement like that per se with regards to storm sewer. And then going further, in the same part of the Texas Code, it discusses odor control. An owner, so that would be the operator of the sewer, shall determine if odor control measures are necessary to prevent a wastewater collection system from becoming a nuisance based upon the potential of the wastewater collection system to generate hydrogen sulfide. And for what it's worth, most wastewater collection systems are quite capable of generating hydrogen sulfide because people eat too many eggs. No, I just made that last part up. A potential odor determination must include the estimated flows immediately following construction and throughout a system's 50-year expected life cycle. Sewage quantity is estimated in a similar fashion as water demand. So in addition to sewer quality and odor, the quantity is actually somewhat of a gift to us. So the same methods that we use to estimate water demand would be directly applicable to estimating sewage capacity requirements. Under the premise that the water that gets into a sewer should only be the water that came into a residence or a building through our drinking water supply. So small residential service area flows are estimated based on population or equivalent residential units and per person contribution to wastewater generation. Larger service area flows are estimated from land use, anticipated population, and similar nearby measured flows. And that concept of measured flows is interesting. Sewage is not measured routinely. We don't build sewage systems and then routinely install flow meters at different points in the system. That may be changing. So that statement may actually be incorrect nowadays. But I'm not aware of it being a routine measurement. Short-term studies are certainly within the capabilities of most engineering firms. Flow measurement is by a variety of tools. Weir's mag meters is it's a shortening of a type of meter that takes advantage of the magnetic field caused by sewage because of the solids and various other materials in it. And acoustic Doppler profiling, if you can put the transducers in such a way that they don't collect too much toilet paper, that can be used. There's a lot of technologies available. The latter two, mag meters and acoustic Doppler, are still on the expensive side. A weir and a water level instrument is pretty simple and straightforward. But bear in mind it is sewage, and if you're putting a weir in, you're putting a flow restriction in. If you're putting a flow restriction in just to measure flow, you're also creating an opportunity for solids and other things to collect and possibly constrict the performance of the system that you're actually trying to measure. So in Texas, the design flow basis is based on the following. An owner must design a wastewater collection system to handle the transport of peak dry weather flow from the service area, plus infiltration and inflow. And we'll look at what those are shortly. The flow calculations must include the details of average dry weather flow, the dry weather flow peaking factor, and the infiltration and inflow. Flow calculations must include the flow expected in the facility immediately upon completion of construction at the end of its 50-year life. So what these bullet items are saying, when we design a wastewater collection system, we're worried about the peak dry weather flow, plus any infiltration and inflow that occurs. So again, if the sewers are correctly connected just to water supply, the peak dry weather flow should be in direct correspondence to the peak dry weather flow to drinking water houses. And the more important thing is it's saying at the completion of construction at the end of 50-year life. So when it's to go in service and when it's to come out of service, and that's to account for changes in population. Bearing in mind that at the end of its 50-year life, that's the future, so we don't really know what's going to happen. We have to make educated, defendable guesses. There's some further requirements in capacity analysis. The owner must ensure that wastewater collection system's capacity is sufficient to serve the estimated future population, including institutional. So if you're going to build prisons, industrial, if you're going to build license plates manufacturing facilities next to the prison, and commercial flows, that has to be included. And must include that the hydraulic capacity of a collection system includes the peak flow of domestic sewage, peak flow of industrial, and maximum infiltration rates. And the collection system must be designed to prevent a surcharge in any pipe at the expected flow. So we had that implication in stormwater, but never explicitly stated, at least in the Texas rules. This is explicitly stated, prevent surcharge. The reason being is if a system is surcharged, that's sewage flowing out of our system into the surrounding environment uncontrolled. Going on in the Texas code, they give us a minimum pipe diameter, which reduces the necessary brains required to get started. So the minimum allowed diameter is 6 inches. Connecting storm drains is not authorized. An owner can use the data from a nearby system. In the absence of such data, we can use these methods for sizing things. The sizing pipe for a new collection system must be based on engineering analysis of initial and future flows. You actually have all the tools to do that. And the new collection system must be sized for the peak flows, which is based on estimated daily sewage flows as shown in figure 4. So I'm obviously quoting straight out of a design document. And here is figure 4, barely readable. And in figure 4, it tells the various categories of sewage sources and the expected daily wastewater flow in gallons per person for each of these categories, and then the expected wastewater strength in milligrams per liter of 5-day biochemical oxygen demand. So for example, a residential subdivision, our expected wastewater flow is 75 to 100 gallons per person. And we expect that water to range between 200 and 350 milligrams per liter BOD5. Mobile homes, on the other hand, have quite a lower wastewater flow, but a higher strength. The lower flow, I suspect, is because if I've been in a mobile home, the restrooms aren't particularly accommodating, so you get in and out quick, so you don't lollygag. Schools, recreational parks, hotels, motels, holiday inns, and so forth are in this table. What's interesting is restaurants and bars have a fairly high biochemical oxygen demand loading. It almost doesn't make sense, but it also explains why food in nursing homes and hospitals isn't nearly as palatable as restaurants because of that extra biochemical oxygen demand, there's a lot more yumminess in the food. Just kind of making that up. So that kind of gives us a brief introduction to sewage capacity estimates. And then there's, like before, there's various different formulas in the Texas Administrative Code as an example. And so I'm going to show 3 of these equations. They all look about the same, but I'll make a comment at the end of the 3. Actually, I'll make it right now. If you're using these various tools to make flow estimates, by all means use them. They're legitimate and they're backed up by the Texas Administrative Code, but be very cognizant of the units. So this one is flow in gallons per day. This is the per capita wastewater production in gallons per day, which would have come from the prior table. And B is the number of bedrooms. So this clearly wouldn't make a lot of sense to apply to a chromium treatment, a chromium plating factory, for instance. There's another equation that's stated here. In this case, the flow is in gallons per minute. And we have a rate factor that's, we look up in an associated table, and then the number of equivalent dwelling units served. So they look like almost the same, except they're using different letters of the alphabet. You have a Q, an X, and a B. And this one you have a Q, an A, and a B, and the magical number N. But the gallons per day, gallons per minute. So again, be very cognizant of the various units. And so here's yet another equation in the code. Q, A, P, and B. This one's in gallons per minute. P is in population served, and I'm pretty sure it's going to be in thousands, but I'd have to go look up the formula again. And it doesn't matter which one you use. Just be cognizant of the units involved. Other jurisdictions other than Texas are going to have similar kinds of estimation guidelines. And finally, the bullet item that I've just been harping on for the last few seconds, the units of each of these equations, which have similar mathematical structure, are different. One produced estimates in gallons per day, while the other 2 are in gallons per minute. So as a design engineer, it's imperative that you know the units your equation is supposed to be producing and can back that up by citation. So if I were to apply, for example, this equation in a design analysis, I go ahead and state the equation as it is right here, apply it in whatever my design is. But I would have a reference in my report that explicitly states where that equation came from, and as written here, the exact units. If we have cause to model a sanitary sewer, SWM is an as appropriate tool as anything. Pretty much can treat it the same as stormwater. If we're curious about the hydraulics working through a treatment plant, we could actually use SWM to model that. It'd take a little bit of thinking, because the reactors in a treatment plant would probably be replaced with rectangular channels of appropriate length, width, and depth. Sumps would be storage nodes. Pumps are pumps, and this could be useful if you needed to draw a hydraulic grade line through a plant. Although generally what's done is the head losses between unit processes are looked up in a design book and use that to get total head loss to the plant, and that's how that's done. We just get the head loss coming into and leaving a plant. But occasionally there's cause to want to be able to look at that at different flow rates, and SWM is probably as good a tool as any to do that. So remember in the design code that we just looked at some pieces of, it said we had to account for inflow and infiltration. So let's go ahead and define what's meant by that. And in that context, what the document means inflow is by definition direct connections to the sanitary sewers. And examples might be a roof gutter or a French drain that's connected to sanitary sewers. And in practice, such connections are not allowed. That doesn't mean they don't happen, but they're not supposed to happen. And then infiltration is leakage into the sanitary sewers through things like cracks in the pipe and an unusually high water table, leaks at joints, and leaks at junction boxes. So here's a cartoon that's showing some of the different possible entry points into our sewage system. So here's our sewer main. That's where we want all the water to end up. We're using red sewage, which would have been good for Halloween, but getting on to, so there's our sewer pipe. It's potential we could have an access port, which they're calling a viewport with a cap. That'd be like a clean out. And if that cap is somehow compromised and surface waters can find their way down, that would be an example of inflow, a direct connection. Another example of inflow might be a driveway drain where surface water from the driveway drain makes its way out here. Kind of like Super Mario, huh? And on out to the system. We could have a floor drain in a house that's directly connected to the sewer system, and with a high water table leaking into this basement, it gets into the sewer and makes its way out. That would be infiltration. Some other examples of infiltration would be a drain at the bottom of the house. And so those would be the types of infiltration that we don't want to have happen. The floor drains kind of, those are bad. That's what the red X is, bad, dirty, no. Oh, and a downspout from the roof. Now, other types of getting sewage into the system, going through a sink, going through a commode, that's what they're supposed to do. That's not infiltration in the context of that rules. And going through the laundry sink down here in this basement, that's normal. Sump pump lifting stormwater out of the basement into the sewer, that would be a bad, dirty, no. So we get an X. So that's about all the examples of inflow in this diagram. Let's now look at infiltration. We're going to use a different color. So we use red for that. How about yellow? Sounds fun. So here we have a cracked or broken pipe. Here's our water table up here. So is the head of water at this point bigger than the head right here? Y for yes, N for no. Question mark for I don't know. I'm going to go with a yes. There's more head because the elevated water table, and if there's cracks in the pipe, then that water can get into our sewer system. That's called infiltration. That's this guy. We can have bad joints, and so no matter how much omega-3 that we get and various good exercise and other stuff that's sold on late night TV because you're an insomniac, you have leaking bad joints that gets water into the sewage system. Same here for a leaking connection. And I think there was one other, that one's on purpose. Yeah, those are our examples of inflow and infiltration. Inflow, direct connection. Infiltration, leaking into the system through cracks or poorly sealed joints or other kinds of bad connections. Or in fact, many, many years ago, I did some field work at a place outside of Houston where their sewer system had essentially a clean out like this that was directly connected to the surface. And the intent was it was an unfinished part of the subdivision. And for whatever reason, the contractors, builders had left that unconnected and open. And it was clear to me from the drawings that it was intended to connect to a different part of the subdivision. And somehow nobody thought to pile up concrete bags in it and close it off for the later expansion, which was years later. So they had a terrible time making their treatment plant work because they kept getting too much water. As soon as we found that location, we blocked it off, and then all of a sudden the system worked like it was supposed to. So that was probably the best research money that municipal utility district ever spent. So here we have another picture, and this time we'll play together now. So I'm going to go ahead and bring up a pen, and let's pick a good color. Oh, blue. Oh, I was hoping I'd make the pen bigger, but I can't. And let's try to identify the different properties of inflow and infiltration. Oh, somebody's already done the work for us. Inflow is red, infiltration is blue. Okay, well, never mind. We don't have to play along after all. So here we have a roof drain connection. Whatever color I picked was a terrible color. There we go. Roof drain connection, that's a direct connection to the system, so that's inflow. An uncapped cleanout, that's a direct connection to the system, inflow. A storm cross connection, so that would actually be illegal in the context nowadays. That those aren't supposed to exist, and that would have been how combined sewer systems were built in the past. So storm connection would be direct connection from the storm sewer into the sanitary sewer. That's inflow. A faulty manhole cover or frame. So if the manhole cover doesn't sit in the ring just so, it makes a pretty big gap and water can get in pretty easy. So there is another direct connection, and there's 4 of them in this picture. And if we had a connected foundation drain, in this case, they're considering that infiltration. That's kind of a tough call in my mind, because that could also be arguably inflow. But because the water has to work its way through the soil, I can sort of see why they chose infiltration. We could have a broken house lateral, so if there was a break in here, that gives water the ability to get into it. So that's another infiltration. We could have a root, and it breaks into a lateral and creates another path for water to get into our system, infiltration. And at our faulty manhole cover, we have all these cracks, and those provide avenues for surrounding groundwater to get into our sanitary sewer system. And we get enough dilution and our water doesn't stay so brown anymore. So that was intended as our brief introduction to sanitary sewer systems. And what we'll do on Thursday is we're going to go look through those Texas design guidelines, and a few others that I can dig up, and observe the commonalities and differences between different jurisdictions. But you have most of the meat of the material. If you've studied the SWM model at all, you'll notice that it has an inflow and infiltration component built into the model, and it's exactly for application to these conditions that were depicted in the presentation. That was all I had prepared for today. And if there's any questions, now would be a good time to ask because we have a little bit of time. And if not, we'll call it a day. I'll wait a few seconds. I know there was concern on the exam. I'm going to go ahead and manually handle the EPANet problems because after I got the emails this weekend, I think I had pointed to the wrong input file. So while you all were in good faith trying to answer those questions, none of the correct answers were available to you. So any answer you gave would have been marked wrong. And so I will manually deal with those. Yes, yes, Yuan, we can take care of that after this call. Any other questions, anyone? Okay, well, I hope you enjoyed what was a relatively easy day today. You do have, you will have another homework assignment coming up, which will deal with detention pond design and modeling it in SWM. That'll be pretty easy because it'll be just like the lecture. And there's also one going to be coming up regarding the next step in the Somewhere USA subdivision, getting the sewer drainage. And then finally, put together a report template so you can tie all that stuff together and have your Somewhere USA design turned in as an assignment. There will be, let's see, one more exam. I think I'm supposed to do it. No, I'm not in the same restrictions in this class, but it'll be largely just on SWM stuff in the stuff since we started the open channel. So it should be fairly straightforward. Are there office hours? We keep the highest attempt. Sweet thing. Yes, we can schedule office hours, Cole. Not today, but tomorrow, sometime. If you want to suggest some availability, I'll pick what you suggest and create a Zoom invite for you. And then Lane, yes, I'll keep the highest attempt. I'm not here to ruin your life. COVID did a good enough job of that. I don't need to help along anything. All right, so I think that answers most everybody's concern. And with that, I'll go ahead and end the phone call today and get this video. Good, I was recording. Get this video posted and wish you all a good afternoon. It looks like it's a beautiful day outside, but it's cold. Maybe it's warmed up by now. So good day, everyone, and thank you very much for your attention and sticking this out. See you on Thursday, and until then, so long. Jan, why don't you just stay on, and I'll wait till everyone else logs off.
All right, that's good.
This is hard for folks to disconnect, but they're supposed to. Well, I'll turn the recorder off. We don't need to record our meeting.